We may take the moon for granted, but what a sight it is to behold in our sky. It's big enough and close enough to us that we can easily make out surface details with the naked eye, like the dark mare and bright craters. Just looking at it through a telescope is impressive enough. However, what I'm about to show you in this video will make the telescope view pale in comparison. You see, we are fortunate enough to have not only visited the moon, but also have an orbiter around it right now with a powerful camera that has been scanning the surface since 2009. So what has it seen? I'm Alex McColgan and you're watching Astrum. Stick with me in this video and I will show you some of the LRO's most recent impressive and puzzling images of the moon. Let's start off with an innocuous little unnamed crater. As you can see, there are plenty of tiny craters within it. And this crater is within another crater again. Maybe you can see where I'm going with this. Zooming out, not only are these craters in another crater, but apparently they are contained within two very nicely aligned craters. Or is that really what this is? Well, we aren't sure. Both of these craters are named as one, the Belle E crater. This peculiar type of crater is known as a donut or concentric crater. It is possible that they are the result of two impactors aligning up nicely, but further investigation suggests otherwise. If they were the result of chance collisions, then there should be a random distribution of concentric craters around the surface of the moon. However, that is not the case. Have a look at this. The population of concentric craters actually clump up around certain areas, especially around the edge of this region of the moon here, called Oceanus Procellarum. Another factor to consider is that most of these craters are of similar ages. Looking for clues in the crater itself also reveals something interesting. This outer crater should be around twice as deep as it currently is when comparing it to other similar sized craters around the moon. Now, while a few concentric craters on the moon will certainly be the result of double impacts, the location, age, and depth of most craters means that something else must be at play. One theory is that some of these impacts occurred during a time when the surface of the moon in this region was in a state in between solid and liquid, with a consistency similar to cool lava or honey. As the impact happened, it caused ripples which propagated outwards, but then stopped and never smoothed off until it was fully cooled and frozen in place. Although this is seen as an outside possibility. The most likely theory is that when the moon was more geologically active, craters in the region were pushed up from beneath by magma trying to escape onto the surface. This would explain the shallowness of the crater, and why we see concentric craters mainly around specific points on the moon. However, while this is the best theory we have at the moment, we don't know for sure. What do you think it could be? Now, apart from the occasional meteor, you probably think the surface of the moon barely changes at all. And while you are mostly right with that, we have found evidence that material does move on the moon occasionally. See if you can spot what I'm talking about in this image here as I pan across. This is the edge of a large 32-kilometer wide crater known as Kepler crater, and what you may notice along the crater wall is evidence that landslides have occurred here, with the dark material apparently having fallen down the slope. Let's have a closer look at what's going on by zooming in on the most prominent of the landslides in this crater. The material seems to originate from box canyons towards the top of the crater rim. The material coming down here is clearly very fine, certainly less than a meter across, as no individual rocks can be resolved within the slide. However, the largest rocks that got dislodged seem to have all made it to the bottom of the crater floor. What's interesting is that the main mass of the slide seems to actually be made up of many smaller slide masses. Look at these individual trails here. So it probably didn't all happen at once, but is happening over time. The slides were likely triggered by tiny meteors striking the crater wall. These tiny impacts and the subsequent landslides round off the edges of the crater, which is why the oldest types of crater on the moon look so smooth compared to the freshest craters. Here's another puzzle to try and solve. Here we have the remarkable Messier crater. Typically craters are round, but not Messier crater. It is elongated with a slit for a crater floor. What is going on here? The mystery continues if you zoom out a bit. Directly next to Messier crater are two more craters. The one on the left seems much older than the other, as it seems to have been weathered away compared to the fresh impact crater on the right. Did the newer crater just so happen to cover an older one? But let's zoom out again. What other clues can we see? Actually, a big clue are these lines coming away from the crater. These are called rays, and they reveal the direction the debris fell after the impact. On rounded craters, debris can go in all directions, like the ones that originate from Tycho crater. However, here, debris goes in three distinct directions: north and southward from this crater, and only westward from this one. So, what would cause that? Well, the answer is an impactor striking the surface at a very low angle, less than 15 degrees. And in this particular case, it seems like the impactor had already broken apart into three parts before it even hit the moon's surface. Yes, all three of these craters likely hit the moon at just about the same time, even the older crater. What actually happened here is that ejecta from this second crater likely fell directly on top of the other crater due to the low angle of the impact, which means that it has been artificially aged. There are some other really interesting aspects of this image though, like the solidified pond of impact melt found at the bottom of the crater, or this region here which appears to have caved in a bit. The impact melt in the first image also appears to have flowed down towards the left of the image. It really is a fascinating set of craters. Let's have a look at another asymmetrical crater and try to figure out why it has the shape it does. While it could be that this crater is also the result of two impacts, or one impactor breaking up into two just before it collided with the moon, scientists think that this is likely not the case here. Notice the shadows in this image, above and below the crater. It is apparent that this crater is right on the cusp of a peak. Zooming out and looking at the topographical map of the region reveals that this is the case. In fact, this may well have been the tallest peak in the local area until by chance this impactor came along and totally wiped it out. Imagine Everest suddenly being taken out by a meteor. The shape of this crater was probably not only caused by the angle the impactor approached from, but also because it hit this steep slope. It might not look that steep from the oblique angled shot. However, over only about 20 kilometers, there's an 8-kilometer difference in elevation from the peak here to the bottom of this nearby crater. In this next image, there's not too much to see. The only thing visible in this wide expanse is this peak, basking in the light of the sun. Why is this significant? Well, this peak is on the rim of Apenus crater, a crater found near the North Pole of the moon. Future colonies on the moon will be located somewhat near the North and South Poles, because tucked away at the bottom of the craters here, where the sun never shines, are large pockets of water ice, essential for any colony to subsist off of. Water can be used for drinking, washing, cooking, and farming, plus breaking down the H2O into oxygen and hydrogen provides breathable air and rocket fuel. These poles also have the added benefit that there are peaks here that are almost always in the sun, unlike other parts of the moon, where the day and night cycle is 28 days long. 14 Earth days in constant darkness is not good for a solar-powered power system. A peak like this one, however, poking out in the sun while the surrounding area experiences nighttime, would be an ideal location for solar panels and powering a colony there. It's not a perfect solution, as peaks like this one will eventually also become covered in darkness depending on the time of year, but 89% of the time is definitely better than other regions on the moon where you'd get sunlight for roughly 50% of the time. I'll just leave you with a couple more islands in the darkness, this time from the far side of the moon, found in Bar crater. These are the central peaks found in the middle of this 80-kilometer wide complex crater.
Do you believe the moon to be barren, grey and uninteresting? Well, to me, that couldn't be any further from the truth. The moon is packed full of secrets about its past and has clues dotted all over its surface, which gives us information about how it formed and evolved over time. From global events that created some of the largest craters in the solar system, to tiny hills exposing layering in the moon's crust. Each helps us get a better picture of our closest celestial neighbour, and as a result, expands our understanding about the formation of the solar system as a whole. It's no wonder then that NASA has a spacecraft called the Lunar Reconnaissance Orbiter, which is in orbit around the moon right now, mapping out its entire surface. I'm Alex McColgan and you're watching Astrum, and in this episode of the LRO series, we will investigate some of the most unusual terrain found on the moon's surface, and hopefully I'll be able to make the grey, barren and uninteresting world into something fascinating and wonderful for you. Let's start with a place rich in incredible contrast. This oblique angle shot is of Jackson Crater, sadly not visible to us on Earth as it is on the far side of the moon. A bit like Tycho Crater on the near side of the moon, when it formed, it created a ray system stretching over 1,000 kilometers. Ray systems form when particularly fine material is ejected far beyond the crater rim, although their formation is still being studied. Jackson Crater itself is about 70 kilometers in diameter, and due to its size, it is a complex crater, as can be seen by its terraced walls and uplift in the central region. This crater is actually tilted. The east side of the crater is 6,000 meters in elevation, and the west side is only 3,000 meters high. The base of the crater has an elevation of 1,000 meters, and the peak comprises of material that was pushed up from another 1,000 meters down. Some of the dark patches you see along the walls are shadows due to the sun's angle in the sky, but there are also sections of darker materials compared to the predominantly lighter coloured ground, although it's not as light as this image would have you think. Your viewing angle and the angle of the sun play a big role in how contrasts appear on the lunar surface. Focus here on the central peak in this image. We'll now switch to a top-down perspective of this same peak, taken at a different time of the lunar day. Suddenly, the crater basin and the tip of the mountain appear much darker than before. But a side-by-side comparison does show how the differences in contrast can be seen in both pictures. And that's not the only optical illusion the moon can trick you with. Have a close look at this image. What does it appear like to you? Are these regions of inverted bubbles? Or are these sections actually rising higher than the wiggly textured material surrounding them? Well, for the longest time, I could only see it's inverted. But maybe if you look around the image, suddenly it will switch perspectives for you. What type of image did you see first? Are you like me and need proof it's not actually inverted? Well, have a look at the same region but from a different angle. Seeing it like this makes me wonder how I could have seen anything else. This is a small region on the moon called Inner. It's only 2 to 3 kilometers wide and 64 meters deep, and no one really knows how something like this formed. It's one of several similar regions on the moon, although this one is the most prominent. To a certain degree, a similar optical illusion can happen with small craters. Do you see domes here, or craters? Sometimes rotating the picture can help get the right perspective. That's why the LRO is so useful in my opinion. Not only do we get top-down views, but oblique perspectives too. Moving on to another unusual lunar region, let's have a look at Komarov crater. This crater would be pretty normal by lunar standards were it not for the fact that it has huge fracture lines running across the base. Komarov crater itself is even bigger than Jackson crater at 95 kilometers in diameter, meaning these are up to 500 meters deep and 2.5 kilometers wide. It is believed that 2.6 billion years ago, magma built up under the crater, causing large amounts of pressure to fracture the crust, although it appears that the magma never made it to the surface, meaning the fractures were never filled in, and it remained like that ever since. But although it didn't happen in this instance, there are examples on the moon of magma breaking through and pooling on the surface. One such example can be found west of Plato crater, a large 100-kilometer wide crater seen towards the north of the moon, visible with the telescope or binoculars on Earth. This image has a few rather spectacular points of interest to see, the obvious one being this channel which cuts through the ground. This section here is a lava vent, back when the moon was a lot more geologically active. Running out of the vent in a southwesterly direction is something known as a rima or a relay. These are channels cut out by lava melting and eroding its way down the slope, kind of like a river on Earth. To the east in this image we see the crater rim of Plato. Plato itself was likely filled with lava at some point, as the base is darker and smoother than the regions northwards. However, in this image we can see that a huge section of crust has collapsed down from the crater wall, creating a 24-kilometer wide slump block. In other words, this section was once connected to the higher plane. However, it has since collapsed under its own weight, breaking away and falling somewhat into the crater. Let's have a look at one more crater. This breathtaking view is from the Apollo 15 mission overlooking Aristarchus crater. Aristarchus is seen towards the northwest of the moon, and although Aristarchus is only 40 kilometers across, it's bright enough to be seen with the naked eye. From Apollo's viewpoint, we can see a really wide-angled perspective of the crater. Surrounding it are more relays and lava vents, and a small ray system can be seen extending away from the center. From this angle, with the shadow extruding out from the rim, you get a sense of how deep this crater is. This complex crater has prominent crater walls. However, the uplift found in the center seems pretty small. From LRO's perspective, we have a much higher resolution view of Aristarchus again, and we can have a close examination of the walls and crater base. The walls are similar in appearance to Jackson crater. However, looking at the peak towards the crater's center reveals some major differences. Not only is the peak much smaller, it also has a banded pattern, exposing layers in the crust that would have otherwise been hidden hundreds of meters down. The base of the crater was also likely to have formed from molten lava, rock melted by the impactor. Fracture lines from rapid cooling are evident all over. And looking at where the walls meet the crater base, you can easily imagine how this base was once a liquid. Let's have a look at one last image. This area is known as Mons Carpatus, and what's immediately apparent here are the variations in contrast again. Generally speaking, looking at darker regions on the moon indicates older material, but it also indicates what the material is comprised of. The darkest regions in this image are thought to have formed from explosive volcanic activity over 3 billion years ago. Lava would have also flown down through valleys like these ones. Also sprinkling the surface are white dots. These are small impact craters, and appear white as they are a lot more fresh than the surrounding regions, and space weathering hasn't had an opportunity to darken them yet.
The Moon. Earth's natural satellite, orbiting approximately 384,000 kilometers away. A celestial object that scientists have studied for thousands of years, using its regular motions to mark the passage of time in calendars. Its dependable rhythms helped ancient civilizations to track when to plant crops, and its waxing and waning phases cemented the moon's place deep in the heart of symbol and tradition. It's a wonder, a necessity, and a curse. While the moon's desolate beauty has captured the vision of poets, it also brings desolation. There is one lunar rhythm that is not helpful to us, a 19-year cycle that brings unexpected floods and ruin. And NASA scientists are worried that in the middle of the 2030s it's about to hit its hardest yet. For ecosystems that are adapted to it in the right way, this won't be a problem. But how adapted are we? I'm Alex McColgan and you're watching Astrum. Join with me today as we learn about the innocently named Lunar Nodal Cycle and why we need to start developing a much better understanding of the fluctuating behavior of our moon if we are to protect ourselves against its dangers. Much like the sun, the moon is an inescapable part of life on Earth. The moon has an immense impact on our planet. You likely have already heard how its cycles influence our wildlife, affect our climate, and create tides. We tend to imagine that the moon and the Earth's gravities cause them to circle each other in a relatively stable, synchronized harmony. But, as is so often the case, nature is not as simple as we imagine it. Instead, every 18.6 years, the moon's orbit undergoes a subtle revolution, a shift in its alignment between us and our sun that causes high tides to grow even higher, tipping us over the edge into dangerous flood territory. But let's delve into what this subtle revolution is. Its name is the Lunar Nodal Cycle, or the precession of lunar nodes. This complex name refers to a specific feature of the moon's orbit of the Earth. You likely know that every 29.5 days, the moon orbits the Earth. However, this orbit is not flat, or, to be more specific, there is a 5-degree difference between the angle of the moon's orbit and the ecliptic plane, the 2D plane on which the Earth orbits around the sun. For half of the month, the moon is slightly higher than the plane of the ecliptic. For the other half, it drops below it. Naturally, this means that there are two crossover points, or two nodes, an ascending node and a descending node, that mark the point where the moon goes from one side over to the other. And it is these nodes that move over the course of the 18.6-year cycle, slowly rotating around the planet in one complete revolution. The nodes themselves are what causes the problem. To understand why, let's recap what we know about tides. You may already be familiar with how the moon's gravity pulls the Earth's water towards it, causing a bulge in sea levels on the side closest to it that we call high tide. You likely also know that this happens on the side of the planet furthest away from the moon. Rather than being caused by gravity, this second bulge is caused by centrifugal forces, as the Earth and the moon's gravitational pull on each other causes them to behave like two dancers holding each other by the arms and spinning across the dance floor. While it's mostly the moon moving, due to the Earth being much more massive, the Earth is also swung around a little. The water behind it is thus trying to fling off into space through its raucous spinning, causing the second high tide. The sun also has a role to play in tide formation, albeit to a lesser degree. It's a bigger mass, which would cause a greater pull if it were closer, but its further distance means that the sun's effect is only 1/3 as big as the moon. When the moon and the sun are aligned, we get extra large tides called spring tides. This happens 6 to 8 times a year. When not aligned, they partially cancel each other out, causing smaller tidal extremes known as neap tides. So now consider the influence of lunar nodes on this tidal tug-of-war. During spring tides, the pull of the sun and the moon working in unison causes the highest tides and the largest risk of floods. However, the sun and the moon are never more aligned than they are at a node. During the rest of each 9.3-year phase, they are not quite tugging in the same direction, so tides are more temperate. At a node, that's where things get more serious and risk of floods become highest. The last time this alignment occurred in September 2015, the UK and the US both issued major flood warnings to its citizens. In September itself, there were floods, albeit minor ones, but it was only when heavy rain combined with the strength of the lunar nodes a couple of months later that the real damage was inflicted. In the US, in October, South Carolina saw flash flooding that caused property damage and people having to be rescued by emergency services. At the end of December 2015, the UK was hit by some of the worst floods it had seen in a century. Combined with the power of Storm Desmond, flooding and storm damage caused an estimated £1.3 billion in damages. These floods can be highly damaging, but that in and of itself doesn't completely explain NASA's worry for the upcoming alignment in mid-2030. There is an extra element at play beyond the regular rhythm of this rising flood risk we have been seeing through the course of human history. Unfortunately, the next node's alignment with the Sun promises to be particularly devastating. The danger is that this phenomenon is combined with an already strained system, even more strained than it was in 2015. Climate change has resulted in steadily rising sea levels. When the next node aligns with the Sun in the mid-2030s, this will likely lead to a dramatic increase of floods on planet Earth. Worryingly, a new study led by NASA's Sea Level Change Science team predicts that almost all US mainland coastlines, Hawaii, and Guam will have a huge leap in flood numbers when this happens. Some predictions claim this node alignment could cause 4 times the amount of flooding from one decade to the next, which will damage infrastructure and change our coastlines around the world. This means human life will inevitably be affected by these floods, impacting shelter, clean water supplies, electricity, as well as the increased risk of waterborne disease outbreaks like hepatitis A and cholera. Plus, the receding floodwater can create stagnant pools of water where mosquitoes gather, which can spread other diseases like malaria. This has a knock-on effect on economic issues, as these natural events can make coastal life unaffordable, with increased cost of insurance on these homes, or an inability to find insurance at all, which could cause a reduction in asset value in the community. Consequently, this lunar nodal cycle will damage the quality of life in coastal communities, where infrastructure may not be rebuilt or adapted to this force of nature. It's not just bad for humans. Ilya Roshlin, a visiting professor at Rutgers University, analyzed that the peak of the lunar wobble, where high tides are higher, can drown salt marshes. Salt marshes are a habitat for a range of species, such as invertebrates, and these floods can cause these creatures to drown, which means that other species like fish, seabirds, and others who rely on invertebrates to survive also suffer. And they aren't the only ones that rely on salt marshes, as salt marshes hold a multitude of marine life, which includes 75% of all fishery species. This means that the lunar wobble impacts the food chains of humans and animals, causing disturbances to their natural habitat and impacting their populations. While this all does seem fairly doom and gloom, it's interesting to note that not all ecosystems on the planet are negatively affected by flooding and high tides. Ecologist Neil Saint-Alain of Macquarie University analysed that the lunar nodal cycle impacts heavily on the expansion and contraction of mangrove canopy cover over most of the Australian continent. The analysis showed that the peaks of the lunar nodal cycle coincided with the cover of the mangrove canopy. It showed that when the lunar wobble is at its minimum phase, it causes the mangrove ecosystems to become very dry, which leads to thinner canopy cover. Yet, when lunar wobble is at its maximum phase, mangrove cover increases. Mangrove canopies are beneficial to Earth's environment as they are complex ecosystems that fight against climate change, protect wildlife, and shield coastlines. They can also absorb 4 times as much carbon dioxide than rainforests of the same size. Their growth is vital to the welfare of our planet, so it's not all downside. Still, it's clear that if we don't plan ahead, coastal cities and environments will face a serious crisis. The all-important question, then, is what can we do about it? One method is better protection. As mentioned previously, the protection and restoration of mangroves can act as a shield against flooding, as they can mitigate the vulnerability of communities on the coastlines. More specifically, mangroves can avert damage by decreasing the height and energy of waves as they pass through mangrove forests. The above-ground roots and branches diminish the height of the waves, and thus the waves lose energy, ultimately stopping the waves emerging onto the seabed and engulfing the sediments. The mangrove's roots and branches also reduce wind energy, which can stop the formation of waves. According to reports, densely packed mangroves can halve the height of a wave through just a 100-meter passage. For comparison, in an open forest where roots and branches are more sparse, it would take 500 meters for a wave to halve its height. So preservation and reforestation of these mangroves or plants with a similar capability can become a great shield against upcoming floods. Another possible solution is to learn how to live with these flood-heavy conditions, working with nature rather than against it. For example, let's take a look at the flood defenses in the Netherlands, where 1/3 of the country is below sea level and another third is at risk of flooding. They've built infrastructure that works with water and manages the rising sea levels. They do this by designing facilities like polders. Polders are bits of land below sea level that have been reasserted from a body of water. It's always fully or partially surrounded by an embankment to keep the water out that comes from either the sea or a river. These polders offer a network of drainage canals and pumps to manage water levels by disposing of excess water and running water back to the sea or river to make sure that the water doesn't run over land. Polders can be used to protect houses, farms and factories, and thus are used a lot around the country. The Netherlands also built dams and utilized sand dunes to create ways to stay dry in their swampy land. This shows that there are ways in which we can observe nature and live alongside it. So, the bad news is, behind its ethereal beauty, our moon hides a power that, if just so combined, is set to overwhelm humanity's coastal settlements. However, there's always a bit of good news too, as knowledge is a power of its own. By understanding our plight, we can look for solutions, both among already existing ideas and ways forward that have yet to be discovered. If we are to endure what is coming, it's high time for us to use our innate creativity and drive to adapt and survive, to work with our planet rather than against it. With so many asteroids hurtling around the solar system, it's a wonder that Earth only has one moon. Because beyond the inner solar system, the gas giants have a lot more, some of which are regular moons, plus a lot of irregular moons. They are called irregular because their orbits do not follow the orbital plane of the planet, instead following a distant, inclined and eccentric orbit, even sometimes orbiting retrograde to the regular moons. The main reason for this difference is that irregular moons are mainly captured objects, asteroids that were orbiting the Sun before they approached too close to a planet and got captured by the planet's gravity. So what about Earth? Well, I can announce that Earth now has a second moon, called 2020 CD3. But it probably isn't worthwhile trying to spot this one in the sky. It's tiny, only 2 to 4 meters across, and also very dark, a type of asteroid known as a C-type or a carbonaceous asteroid. These types of asteroids are as dark as wet asphalt.
This moon, like the irregular moons of the outer planets, is a captured asteroid that's been pulled into orbit around the Earth. It was probably captured as recently as 2017. Although, before you warmed to the idea of Earth having two satellites, it seems that this is only a temporary relationship. Astronomers are expecting it to escape Earth's gravity again by April 2020. This is due to its chaotic orbit. It never really got settled into a stable orbit, and so will be ejected again in just a few months. A very similar thing happened in 2006 with an asteroid called 2006 RH120, where Earth had a second moon for just short of a year, before again it was ejected. And just like back then, once this one leaves Earth's orbit, we'll be back to just the one natural satellite. Or will we? There is another asteroid orbiting Earth at a distance of about 9 million kilometers, much further out than the moon, called 2016 HO3. Except, although it's circling around Earth, it's not really orbiting the Earth at all. Instead, it's orbiting the Sun, and its orbit is very similar to Earth's, just a little more eccentric. At some points of this orbit, it is ahead of the Earth, and 6 months later it falls behind the Earth. This is something known as a quasi-satellite, and Earth has 5 of them that we know of. Moons which circle the Earth and are even influenced by its gravity, but without truly being in orbit. And so, unfortunately, they aren't and can't be classified as true moons. We aren't the only planet to have quasi-satellites. In fact, they all might, considering these objects are very difficult to spot. But why do gas giants have so many irregular moons, and Earth only has the one? Right now, anyway. Well, being big and massive is only part of the answer. Yes, the more massive you are, the bigger your gravity. But Earth's gravity is hardly a slouch. It's easily comparable to Saturn, Neptune, and Uranus. So what's the difference? Well, simply put, there's another force of gravity in the solar system called the Sun. Moons in orbit around planets are constantly being tugged and pulled at by the Sun. However, they are within something called the planet's Hill sphere. Within the Hill sphere of a planet, the planet's gravity has more of an influence on the object than the Sun's gravity. And this influence will be different depending on how close you are to the Sun, because the closer you are, the stronger you are under the influence of the Sun's gravity. This means that the Hill sphere around Earth isn't very big, only 1.5 million kilometers. If Earth was closer to the Sun, its Hill sphere would be smaller. If it was further away, it would be bigger. And now you can see why these gas giants have so many captured moons. Their Hill spheres are simply much bigger all the way out there. In fact, Neptune, while not being anywhere near as massive as Jupiter, has a much bigger Hill sphere, meaning it can capture stray asteroids which are tens of millions of kilometers away. In order for Earth to permanently capture an object, it would have to happen in just the right way, likely needing some helpful gravitational tugs from our moon along the way to tame its orbit. And as far as we know, that hasn't happened yet, meaning anything that does come too close only sticks around for a few orbits before it leaves again. So, enjoy 2020 CD3 while you still can. Can a moon have a moon? Well, yes, in theory it can. And yet, we don't see any examples of this in our solar system. So why is that? The first important thing to know is that all celestial objects have gravitational pull. That includes tiny little asteroids, all the way to giant stars or even black holes. The mass of an object dictates how strong its gravitational pull is. A region around an object where its gravitational influence is greater than any other celestial object near them is called its Hill sphere. Due to the mass of our Earth, it has a Hill sphere which has a radius of 1.5 million kilometers, meaning that if you were within this Hill sphere, you would be pulled more towards Earth than towards the Sun. If the Earth was closer to the Sun,
its hill sphere would be smaller, and if it was further away, it would be larger. The Sun also has its own hill sphere, which contains the entire solar system. Its hill sphere is massive, almost 2 light years radius, as the nearest celestial object its gravity is competing against are the stars. Which means, in a way, everything orbiting our Sun is the Sun's moon, or rather, its satellite. The term moon is really reserved for satellites of planets. So why don't moons also have natural satellites? Well, lots of moons are extremely close to their parent planets, meaning their hill spheres are very small. Let's take our moon as an example. Against the Earth, the hill sphere of the moon is only 60,000 kilometers radius, or only 1/6 of the distance from the moon to the Earth. Moons like Io have an even smaller hill sphere, as it is competing against the gravity of Jupiter. This makes it quite hard for moons to capture an object, but not technically impossible. So surely there must be a moon that has a natural satellite somewhere, right? Well, most moons also have one other major problem. They tend to be tidally locked to their parent planet. Because of this, any satellite that orbits a tidally locked object will have its orbit decay from tidal forces until it eventually crashes into the moon. Now, this still takes a lot of time over astronomical standards, but it means if any of the moons in our solar system did have a satellite at one point, chances are that it has since crashed into it. This leaves one question, I think. Why don't moons of planets also eventually crash? The difference is that none of our planets are tidally locked to the Sun, as they are far enough away from the parent star, which means their moons have a stable orbit. This is one of the reasons we believe that none of the TRAPPIST system planets have moons, as they are so close to their parent star that we assume the planets are all tidally locked. I hope this didn't disappoint you too much, so I'm going to leave you with this. There are some other curious objects in the solar system, far away from any other object, so that they aren't tidally locked to anything. This particular asteroid, called Ida, looks like a standard 30-kilometer wide asteroid as seen by the Galileo spacecraft, but you might notice this little blob here. This is actually Ida's moon, Dactyl. It's only 1.5 kilometers across and orbits only 60 kilometers away from Ida. We don't know especially how stable this orbit is, but a very cool thing to observe nonetheless. We are used to tectonic activity on Earth, it being a daily occurrence somewhere on the planet. But what about our closest neighbor, the Moon? During the Apollo missions, seismometers were left on the Moon to detect the presence of moonquakes. From these instruments, we now know that the Moon does have quakes, and relatively frequently too. But unlike Earth, most can be attributed to meteors striking the Moon's surface. Although, there is also evidence to suggest that a small percentage of these quakes could be due to the Moon shrinking and contracting. Early in the solar system's life, most of the celestial objects were hot, a result of the process of how they were formed, and followed up by a period of heavy bombardment. Since then, impacts have become much less frequent, and these objects, including the Moon, have cooled down. As something cools, it contracts. Photos taken by the Apollo missions imaging the Moon's surface, and photos from the current lunar mission, the Lunar Reconnaissance Orbiter, show that the Moon is covered with these kilometers-long ridges, or Lobate Scarps, which can rise up to 100 meters high. Scientists believe they are connected to the Moon cooling. They predict that these scarps are caused by thrust faults, faults caused by the lunar crust being pushed together until it gives, causing a distinctive scarp on the surface which is steep on one side and shallow on the other. It could be that some of these moonquakes detected by the old Apollo missions
are caused by these thrust faults even today. The images that we have of Lobate Scarps and the Moon show that they must be pretty young, certainly formed within the last 100 million years. We know this because they can cut right through older craters which are big enough that they would have likely formed billions of years ago, not recently. Tidal forces from the Earth could also influence the location of these scarps as the Earth's gravity pulls on the Moon's crust. Here you can see the location of the scarps across the Moon, and the arrows represent the direction of pull caused by the Earth's gravity. Even with all these influences, however, it is thought that the Moon has only shrunk a total of 250 meters since it was formed. Mercury, on the other hand, has had a much more tumultuous past. It is thought that early in its life it was actually a molten world and has since cooled and solidified. Mercury is also special in that it has a massive neighbour exerting an incredible amount of tidal forces on it: the Sun. This means its contractions were much bigger than our Moon's. Here you can see one such Lobate Scarp, which is about 2 kilometers high and hundreds of kilometers long. In comparison to the Moon shrinking 300 meters, Mercury is thought to have shrunk by up to 4 kilometers. So yes, the Moon is shrinking, but we don't need to worry about it disappearing anytime soon.
I bet you didn't know the Moon did this. This isn't the camera moving, it's a real time lapse of the Moon. While the same face of the Moon roughly faces the Earth at all times, there's much more wiggle room to that than you might think. By taking a time lapse of the Moon as it circles the Earth over the course of 1 month, we discover the truth of its wobbling path. Go home, Moon, you're drunk. A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape, a place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.